All right, everybody, welcome back. This is part 2 of the demonstration for the threaded shaft project for Machining 210 at Laney College. Last time we got this far, so we faced both sides, put centers in there, and then we turned this 875 thousandths diameter. Now we're going to go ahead and do steps number 10 through 13, which is going to be turning the other side of the part. So there's another diameter 745 that goes back 3 inches, and then a 618 thousandths diameter that goes back 1 inch. The first thing that we have to do actually is put this between centers. Remember that the idea here is that we're going to sandwich the part between two conical centers, and one of these is going to be the tailstock center, this live center. It's called a live center because it's got bearings in it so it can spin independently. Actually, they used to have a different type of center before they invented these things called a dead center. So like this is a dead center right here, and you can see hopefully that they are basically the same thing, except that the live center can spin independently, and this is really nothing more than just a piece of hardened steel that's got a 60-degree cone ground on the end of it. This works just fine. The only issue is that now you've got relative motion between the cone in the part, the center in the part, and the dead center, right? And so you have to lubricate that, and over time there's going to be wear. As opposed to with this style, because the entire cone, the cone on the center can spin freely, it can spin with the part, right? And so actually all of the relative motion is inside of the bearings, and so it's just it's a better way to do it, right? A lot less wear on the actual part. But on the other side, right, we need something that goes into the spindle. And we could just, actually they do make sort of centers that go directly into the spindle, because the spindle actually has a taper on the end of it. And so we could remove the chuck and put a dead center in there, and then that would actually spin along with the spindle, obviously on the spindle bearings, right? And so we could do that. But another really common way of doing this that we're going to show you is you can turn very easily a dead center by just putting a piece of scrap material in the 3-jaw chuck. Okay, so that's what we're going to show you now. And all you really need is just a piece of scrap steel. Okay, this is just that same leaded steel, doesn't really matter what it is. Okay, this has to be, a certain length just to hold enough. I mean, that's whatever that is. 2 3/4 of an inch. I mean, it's just a piece of scrap, right? It doesn't have to be a piece of stock that you cut off. It could just be a piece of scrap. And we actually have a big plastic bin over near the stock material rack, just filled with a bunch of these that you can use for yourself. So also it doesn't have to start off being sort of this, just raw, flat face on the end of the piece, right? You could start off with something that already has a cone in it. The only trick here is that every single time we take one of these out and put them back in, we have to touch that cone back up to make sure that it runs true to the 3-jaw chuck, okay? Because these 3-jaw chucks, they're called self-centering, but they're not really self-centering. I mean, they'll center relatively well within a few thousandths of an inch, but they won't center perfectly. And so since how concentric our part runs to the machine is dependent on how true these centers are running, if the centers aren't running true, then our part's not going to be running concentrically, and we're going to have all kinds of issues. It sort of defeats the purpose of using this type of setup in the first place. Okay? So that's why it's really, really, really important to touch this up every single time, and I'll show you that in just a moment. Okay, the first thing that I'm going to do is just go ahead and mount this center in there. And, in terms of stick out, it's going to depend a little bit. But something like, I don't know, it could be 3/4 of an inch is probably okay there. Now the thing is that the cone that you cut on the end here does not need to be a full cone. It could just be a partial cone. And that's because the the cone on the part is actually pretty small, right? So, you know, the cone that's holding it only needs to be slightly bigger than the cone on the part, right? So not super important that you have a large cone on here, okay? Okay, next thing is that we have to adjust the compound, okay? The compound's got to be at the same angle that we want for our cone. And so those centers are 60-degree cones, and so we're going to need to do 60 degrees on the compound. Or actually, we're going to do half of that, right? We're going to adjust this to 30 degrees. Reason for that is that on the cone, the included angle is 60 degrees. So on this thing, the included angle between the two sides is 60 degrees, right? So from center, that means 30 degrees. So 30 degrees on one side, 30 degrees on the other side, 60 degrees between the two. Okay, that's called an included angle. So we can go ahead and adjust this to 30 degrees, and there are these very handy-dandy little marks on the side of the compound right here. You can probably see that in the second camera a little bit better. So there's a little chisel mark right there, okay? And then we have our graduations on the side of the compound. And actually, there's another chisel mark over here, okay? So you can use basically you can set your angle from two directions. So you can set your angle from perpendicular with the spindle axis, or you can set your angle from parallel with the spindle axis, okay? And so for this, we're going to want to adjust it 30 degrees from parallel with the spindle axis, okay? So we're going to use this chisel mark right here. Get that as close to 30 as you can, just by eye. Now, some people would want to adjust it 30 degrees this way, okay? Problem then is that in order to cut the part, we're going to have our tool facing this way. Remember that our tools are oriented this way, right? So in order to cut on the back side of the part, you'd have to orient them this way or something like that, but that's not really what they're designed to do, right? So we need to adjust this so that we can cut with the tools in this orientation. And that means 30 degrees this way. Right there. Lock that down. Okay, now I'm going to go ahead and put a tool into the tool holder, and you can see that the tool is facing a totally incorrect angle here. So we're going to need to adjust that as well. So loosen the top of the tool post right there. And just by eye, you know, there's no reason to get this super close. Actually, anything in this basic area right here will work. You know, just try and get it more or less square, okay? But we're going to be cutting a cone, so you know, it's not really that important here. That's just fine. So we are, just for our own education here, we are currently on step number 10, mounting the dead center in the 3-jaw chuck, which is what we're doing now. Set the compound rest to 30 degrees from parallel with the spindle axis, and then true up the dead center. Okay, so we can go ahead and turn the spindle on. Speed to run this is, you know, same as the, you know, equivalent diameter piece of steel. I leave that up to you to calculate. The issue is that you're cutting a cone, right? So the diameter is constantly changing as you're traveling up that cone. So, you know, base it on the largest diameter just so that you don't burn out the tool. Although it's not, it really isn't super critical here. Okay. Okay, so I'm going to go ahead and position the tool right here in that corner. And so the path that we're going to follow is actually coming from the compound, right? As I move the handle here on the compound, it's going to follow that 30-degree angle that we made, okay? And so where I am right now, you can see I'm just touching the very corner of that part, right? Where the flat face and the diameter meet, okay? Now all I need to do is, and I can take a certain depth of cut either by moving with the carriage or by moving with the cross slide, okay? I'm just going to go with the cross slide, moving, I don't know, let's say 100 thousandths at a time. Put a little coolant on there. So you can see the way that that cuts. Basically, at this point, we just cut a chamfer on the end. Okay, if I go in another 100 thousandths, you can see that every time I take a cut, I get a bigger and bigger and bigger cone. And if I just kept going, you know, I just kept taking certain depths of cut, 100 thousandths or 50 thousandths or whatever at a time, then I would eventually get to the center, right? And I would have a full cone with a sharp tip. Now the thing is that we don't need the full cone all the way on the front of the part, right? We could just have a little cone at the tip that hit like a flat shoulder, okay? We don't need a full cone. And actually, there are some issues with being able to position the part correctly if your center sticks out too far from the front of the chuck jaws, okay? So you don't want this sticking out too much, right? So we'd actually like to keep it pretty close to the front of the chuck jaws. So I'm just gonna cut it back maybe, and who knows, what we may need to change this position. I'll just cut back this far and stop right there. Yeah, this is pretty sensitive to your tool height, as you can imagine. Once you get to the center, if your tool height's not perfect, then you're not going to be cutting at the very, very center of the cone. And it looks like I may be just a little bit low here. We'll see. But you can see that coming off really nicely. I think I may be just a little bit low. Let's see. I'm going maybe only 30 thousandths now. Now I'm just trying to get a nice sharp point on there. Doesn't need to be a perfectly sharp point, because actually the center drill, you know, it has that like little straight section right at the start of it. Okay, so that whole area right there is not going to be touching the cone, so you don't need a perfectly sharp point, but it should be pretty close. Okay, that actually looks pretty good to me. So now I'm going to take a cut of like 10 thousandths or so, 5-10 thousandths, and feed it nice and slow just to get a decent surface finish on there, because it is, after all, a fixturing surface. So it'd be good to have a decent surface finish so that we have more actual material in contact, a greater surface area of material in contact between the two components, the dead center in the spindle and the center hole in the part. Yep. That's all she needs. All right. So let me do a quick check now and just make sure that the part's going to be able to fit up correctly. Okay, so I'm going to remove this drill chuck that we had in there from last time and put in the live center. Okay, clean that up really good, make sure the tapers are clean. Oh, that's got to be out a little ways, right? Okay. All right, so this is what we're looking at. Everything's got to be nice and clean. You know, obviously you don't want to mount this thing with chips in between the centers and the center holes, right? That would just be ridiculous. All right, something like this. That's what we're looking at right there. Okay, that's how it's going to get fixtured. Now, one issue here that you can probably tell immediately is that, you know, this will spin along with the spindle because there's friction between the cone and the center, right? But if, as soon as I start cutting, the cutting forces are definitely larger than the frictional forces here, right? And so you can easily just make this spin relative to the spindle, right? And then that'll chew up that center pretty quickly, all right? So we need some way to positively drive this part, meaning that we force the part to spin, right? So usually what you need is some kind of like physical, mechanical interlocking that actually forces this to spin along with the spindle. And the device that we use for that is called a lathe dog. These are lathe dogs. And you can see that they come in a variety of sizes. Actually, we've got some that are pretty gosh diddly darn big. I mean, that is a pretty big lathe dog. I don't think we even have stock on our material rack that would be able to, that's big enough to fit inside of there, but, whatever. It's nice to have. These are a little bit more manageable, more hour size here. And the lathe dog, as well as having a really adorable name, is a very, very useful tool. And it's also very simple, right? It is essentially just a hole that's got a set screw on it, right? So this is how you mechanically fasten the lathe dog to the part. And then it has this little arm, or this tail as I like to call it, and that actually interferes with the chuck jaws. So the chuck jaws, that interference is forcing the lathe dog to turn, right? And then the set screw is forcing the part to turn, and that's how we're getting our positive drive there. Super, super simple, very, very useful. One thing that you need to watch out for here is that this is a finished surface right here on the part, right? And so even though this set screw has like a pretty smooth, flat face on it, and it's pretty broad, it's still going to mar that surface. It's going to dent it if you screw this down too hard. So we usually use some kind of an intermediary, like a little piece of copper, something like that we wrap around the part, or minimally just put between the set screw and the part, right at the point where that set screw touches. So that's just something that we do to keep the surface finish on our parts looking decent. Okay, so here this little copper shim would just fit in between the end of the set screw and the part like so, okay? And of course it is conformable. That's the reason that we like it. So because this is soft, it won't ding up the part, and it'll conform to the shape of the end of the set screw and to the shape of the part, right? So, these deformable, malleable metal shims are really, really useful for that reason. Or you could use something like this, which is the same material, just a little bit longer, right? And then that just kind of wraps around. Really the way that this is going to work, it's going to get 3-point contact. So it's not exactly a hole. It actually has like a little V on one side, right? So you have the set screw, that's point number 1, pushing the part up against this flat surface and this flat surface, so that's points 2 and 3, right? So you usually don't have as much of an issue with denting or damaging the surface with these flat surfaces in the V here. But, it is better to put a little bit of a shim in there, okay? So actually that's what I'm going to do, because I've got it. Use it if you've got it. And I'll go ahead and cut that too. You're going to need to remove this in order to get at the part. And you can use a bigger lathe dog like this one. Obviously, this will go inside that hole, right? The hole just needs to be big enough to take the part. But the bigger the lathe dog, the more space you're going to need, right? The more likelihood there is that this thing's going to come swinging around and slam into your, compound or whatever it is, right? So try to use the smallest lathe dog that you can. Okay. It's also important that you remember to put the tail of the dog going the correct direction, right? It should be going towards the spindle. Oh, there's a little bit of schmutz in there. Okay. Okay, so just to position the dog, something like that, perhaps, just so that there's a little bit of, mechanical interference there. Watch out for that shim. The dog should be mostly on the surface, but it doesn't need to be fully on the surface axially, right? It should just be mostly. Okay, and then to tighten this down, just use a crescent wrench. Now remember that we're going to be cutting this back about an inch, okay? Because that's how long that 875 diameter is, right? So we have to be able to clear this back to about an inch, right? Which means that you can't have the shim sticking out too far, right? The shim can't be too wide. Also the axial position of the lathe dog is important, not only because you need it to have, it needs to be far enough towards the chuck to interfere with the jaws, but also because you don't want it too far this way so that you won't be able to get your cutter up close enough to finish off that 1 inch length on the 875 diameter. Okay, just a couple things to watch out for. Okay, let me go ahead and flip this compound around again. And now we can move it back to, well, essentially any position. Okay, so like in this case we're at, I know that's 30 again. Why not set it to 30? Or, really remember I mentioned before, it's anywhere between parallel and perpendicular to the spindle axis is fine. So we could just arbitrarily set it at 45 degrees, right? But, I usually set it to like 29 degrees. That's what we use for threading, so, why not? Why not? Doesn't really matter here. Okay. And let me go ahead and reinstall that tool. Obviously, we're going to have to move the tool post again. Okay. Something like that. Now I'm just adjusting it by eye so that it looks like it's, it's square to some line on the, well, really you could use any line that is straight and either perpendicular or parallel. We'll lock that down. Okay, one thing that's really important to note is that you need to be able to get your tool far enough this way so that you can actually get to the start of the cut, right? What if your tailstock stick out is really, really short and your part is a little bit, it's pretty far over to the left here in terms of the position of the tool post on the compound? Well, now I can't physically move far enough to the right to be able to access the front of the cut, the beginning of the cut there, because I'm interfering right here with the end of the carriage and the beginning of the tailstock. Okay, so obviously that's not going to work. So we got to do one of two things. Either we can loosen the tool post and slide it in its little T-slot, right, to change its position, or we can loosen the tailstock and the quill, and then, actually this is pretty easy to do. You just feed this out with the handle like you were drilling, right? And because the quill is actually stopped on the end of the part, then that'll move the tailstock, the entire tailstock assembly, right? Because the quill is stopped on the end of the part. Okay, so you only need to do that so that you can get access to the part. You'd like it to be as short as possible so that you give yourself the most rigidity, right? The least distance between the two supports, the more rigid it's going to be. So, this is a happy medium here between being able to access the part and having a little bit of clearance here so I don't slam into the tailstock accidentally when I'm backing the tool off. Okay, lock the tailstock down. And so now we have enough clearance left to right, but we also need to make sure that we can get deep enough with the cutter, right? And so that just has to do with making sure that the stick out on the tool is enough so that you can get down to your cut before you actually intersect with the front of your tool post or the front of the tool holder on this part of the center right here. Okay, so you have to be a little bit careful with that. And this looks perfectly fine, right? I mean, you can just judge by eye that that looks appropriate. Okay, one final thing that we need to do is we need to make sure that the angle of the tool is appropriate. Okay, remember before we scooted it out just a little bit so that we could get more, we could get closer to the jaw, or in this case it's going to be the lathe dog. So the end of the tool is just basically flush to the tool holder right here so we can get the maximum distance, all for clearance sake. Here we need to adjust the angle of the tool because you know that side cutting angle that we put into the tool there? Basically we made it 0 degrees so that that cutting edge is parallel to the side of the tool. That's what we did. But we can always change that angle there, right? Just based off of the angle that we put that tool in there. So we can give, even though the side cutting angle is 0, we can change what's called the lead angle of the tool. So if we orient the tool like this, then our angle is going off in this direction, right? Which means that we're always going to be cutting a little bit of like a wedge into the part as we're cutting, right? We're not going to be cutting like a flat surface that follows the length of the cut, okay? Not a flat shoulder. And so that has the tendency to actually cause the tool to sort of bite into the material, and it gets dragged into the material as you cut, okay? So a little bit of this angle is okay, but it's not ideal. The nice thing about this is that even though you're not cutting a flat shoulder, square shoulder along the length of the cut, you can always feed the tool back out, and that will clean up that cut. It's like taking a little facing cut on when you back the tool out. So this is actually okay within reason, especially as long as you don't angle this so much that you remove all of that clearance that you put on the end of the tool, that end cutting angle. What if we orient the tool this way? Okay, now the angle is going off at this direction, and so again we don't have a flat shoulder that we're cutting, but actually it's worse than just that, right? Because even if we were to backfeed the tool, there's no way to clean that up because we're putting a chamfer into the part the entire way that we're cutting, right? The entire length of the cut. And so wherever we stop, that shoulder is going to have a big chamfer on it, right? So it's going to be like a tapered surface instead of a flat surface. And there's no way to fix that just by backing the tool out and taking a facing cut. Okay, now for roughing, this is actually kind of desirable because of the way that it distributes the cutting forces. But for what we're doing, trying to cut to a square shoulder, this is not going to be acceptable. So we need to adjust this so that the side cutting angle is either exactly square with the machine, which is pretty unlikely. I mean, it's really difficult to get it right there. I mean, impossible to get it right on. So to me, it's always better to just, tip it a little bit towards this direction. Okay, just to ensure that we don't have any issues with having a chamfered surface on our shoulder. Okay, it's kind of a nuance, but it's really important. Let me just double check to make sure that we still have clearance here to the center of the part, and we do. Good. All right, last thing that we have to do here is just make sure that our part is reasonably tight in the fixture. Okay, so that's just a matter of advancing the quill, okay, so that you take all of that, just put a little bit of pressure between the two centers, okay, so that it squeezes the part. And you want to be able to rotate it freely by hand. You don't want it, rattling around, just knocking around like that. But you don't want it too tight either. You don't want to jam it too hard together because that potentially can force the dead center back into the lathe chuck, or it can just put stresses on the live center or stresses on the part, right? So you don't want to do too much pressure, but it needs to be enough pressure to fully hold the part in the correct location and maintain that concentricity between the two cones. Okay, and so basically what we're looking for is just enough so that you can feel a little bit of tension when you move this by hand, all right, and the lathe dog stays in the position where you set it, basically. Okay, oh, see that would not be correct. That's loose. Okay, that looks perfect. Make sure that you lock the quill down, okay? There are two handles on the tailstock that you need to tighten here. So what we're going to be doing in this stage is cutting this 3-inch length, right, to 745 thousandths, right? and then this 1-inch length to 6/18. Now, when we take that 3-inch long cut, remember that right now there's a lathe dog over here on the 875 diameter, so we need to be able to move far enough over to the left towards the spindle without slamming into the lathe dog, right? So we need to be able to check this in the setup, okay? To check this in the setup, it's relatively easy. We just use the spin test that we did in the first demonstration video. Okay, I'm going to position my tool approximately in the position where I'm going to stop it, right? So I know I'm not really going to be feeding it past that point, so 3 inches from the end, okay, just with a ruler. And then, put this into neutral, and then I should be able to spin this freely without it slamming into anything, okay? And that's my clearance right there. It's only about, I don't know, like 1/4 of an inch or something, so it's not very much. Okay, it's not very much, but it is enough. Okay, so I think that we have checked everything now, and we are ready to go. So we did step 11, installing the lathe dog on the 875 diameter and mounting the part between centers. Now we have 2 more steps to go. Turn the part to 745 and 3 inches length, and step number 13, 6/18 and 1-inch length. Again, the speed is something that you should have set yourself. Okay, so we'll go... We'll go right there, okay? So the first thing that I'm going to do is actually touch off on the end of the part, okay? We're going to set that 3-inch length, right? And this time, we're not just going to be sort of, you know, it's not enough to just make a mark with a Sharpie and cut to that position, right? Because we really want to nail that dimension, and it's a 3.00, it's 2 decimal places, right? So that's plus or minus 10 thousandths. So it's not a super tight tolerance, but there is a tolerance there, and we need to make sure that we hit it closer than we could with just a Sharpie mark, okay? So now we're going to use a slightly different method. I'm actually going to touch off on the end of the part here, okay? And then I'm going to move over exactly 3 inches, and then I'm going to set my dial indicator at that position to 0, okay? Okay. Okay, so I need to position the tool far enough this way so that I'm in, I'm in front of that front face there, so that when I move to the left with the carriage, I will just pull a tiny little chip on there. Remember, it's a finished surface, so all we really want to do is just pull a tiny chip. Okay, right there. That's just touching off. Okay, and now pull it back. So the position where my carriage is right now is the position where the tool is just touching the front face. So if I move my tool exactly 3 inches from this position, that will create another little shoulder right here that has a distance of exactly 3 inches from the front of the part. Okay, that's what we're trying to accomplish here. I could take this dial indicator and put it on the ways of the part and move over 3 inches. Problem is, this only has a total of 1 inch of travel. So I guess what I could do is I could move over an inch, readjust it, move over another inch, readjust it, move over another inch. Well, you know, that's going to get old really fast and introduce an error every single time you readjust this thing, okay? So the way to do this is to use some kind of a standard, okay, that is 3 inches, and then we will set the dial indicator off of that, okay? So that's going to be this 1, 2, 3 block, okay, which is precision 2 inches by 3 inches by 1 inch. It's hardened and ground so that it's within 2/10 of a thousandth of an inch on squareness and all of the size dimensions. And what's nice about that is that we also have our 1 inch dimension here when we go to set the length of the 618 thousandths diameter, right? So normally we would just put the indicator here on the ways and we'd bump it up against the end of the carriage right there, and then we'd set our 0 to that position, right? In this case, we're going to put the 3 inch dimension on the 1, 2, 3 block between the indicator and the end of the carriage like that, and then we'll set our indicator off of the end of the 1, 2, 3 block, right? And then now, right, if I were to take this out, now if I were to move the carriage over to where the indicator was zeroed, I will have moved exactly 3 inches, Okay, that's the gist. Now it's a little bit awkward, right? It'd be nice if we had another set of hands to be able to do this, but we don't. You can get away with it. You just need to make sure that that 1, 2, 3 block is really nice and square up against the end of the carriage there. Okay, make sure that the indicator is not at some weird angle, right? You can just visually line it up with the ways. So the other question here is, where exactly do you position the indicator, right? Where do you position the pointer on the dial on the indicator? It's most convenient, and it makes the most sense intuitively if the 0 is on the top position of the indicator. You don't have to do it that way. It's just, more intuitive, right? Positive is towards the right, negative is towards the left. I mean, at least that makes sense for me, so that's what I'm going to do. But it could be anywhere on there. The other thing here is that I typically give myself an extra couple of rotations, right? I don't just stop at the first 0 on the indicator, like right there. That would be right there. And, this would work. This would work. So all you would have to do is move the carriage until it touches that first 0, right? The only problem is that you can see that, right here it sort of bottoms out at the 50 or maybe 55 point, and so it's got about 45 thousandths before it hits the 0 over here. And that's, when the lathe is power feeding, that's maybe just a little bit too little travel for my taste. I mean, because it's going to go from 45 or from not touching to that first 0 awfully fast. So I'm going to give myself another 1 or 2 revolutions. I usually give myself 2 revolutions. So this is where the first 0 was. I push it in until it gets to the second 0 in the revolution, and then again to the third 0 in the revolution, which indicates that I've made 2 full revolutions. Okay? Just like that. Okay, so now if I pull this back a little bit, you can see it does re-0 every time, right? If I take the 1, 2, 3 block out and put it back in, it does hit that 0 every single time. So now I'm going to just verify that, okay? I'm going to move my carriage to that 0 point, and then I'm just going to check to make sure that I've moved 3 inches with a ruler. Because if I'm going to be off of my location, I'm going to be off probably exactly 100 thousandths of an inch, right? Because that's how many thousandths of an inch I have in my revolutions here. So here we're not touching, and then that's the first 0, second 0, third 0. Okay? Quick check here. That's about 3 inches, and it does look like the end of my tool is right there at 3 inches from the end of the part. Okay, good. Do another quick little spin test and make sure that I've got clearance. Yeah, I do have clearance. It's not very much though. I'm also pretty close to hitting that shim right there, but I'm not going to hit the shim, so it's not an issue. So this looks good. One thing that I'm going to do, just to give myself a little visual indicator here so I know exactly where to stop, is I'm going to put this into gear. Okay, turn it on, and just plunge straight into that diameter. Just to put a little witness mark right there. That's all. Now I have something to follow, right? Some kind of visual indication that, I have a little bit more to go or I have gone too far. Okay, so now that we have our length position where we're going to stop the carriage, now we need to touch off on this diameter and start taking our cuts. So now I'm going to position the tool so that it is directly on top of the diameter and feed in with the cross feed until I just pull a chip. Right there. Okay? And you can see that this whole setup is wobbling a little bit, right? That surface right there is running out a little bit, and that's for a number of reasons. One is that it's just a stock mill surface, right? So it's not particularly round. Plus, when we put those 2 centers in, right, we center drilled the 2 holes on the end, we did that in the 3-jaw chuck. So, those cones are pointing off at different directions relative to one another. And it's only when we sandwich the 2 cones together that we establish this sort of reference axis between the 2 cones that the part is going to be spinning on. Right? So from this point on, everything that we cut is going to be concentric to the axis established by those two cones. But before this point, nothing is going to be running true to that axis, right? So we expect everything, including that 875 diameter, to be running out a little bit. It's not a big deal that it runs out. There's no call out on the print for run out or for concentricity or what have you, okay, for any of these diameters. The only reason that we care about it is because we want to be able to take this out and put it back in and have it repeat every time, so that we don't have to, so that we don't have to finish everything in a single setup, right? Because this is our first project, and we want to be able to take our time with it. Okay, so here you can see that I touched off on one side of the material, but not on the other. Okay, and that's because this surface is running out. Don't worry, as soon as I take a cut, it's going to true up. Okay, I'm going to go ahead and zero the dial on the cross feed. That's 0 right there. Okay, now this should be about 1 inch. Let's check that. Just use dial calipers for this. So that's telling me, yeah, 1 inch and a little change. Okay, so we need to get this down to 745, but I'm going to leave about 30 thousandths of an inch for two final cuts, two finished cuts on there. So 745 plus 30 thousandths is 775. So 1 inch minus 775, we're going to take about 225 thousandths. Okay, so we know that we have about that much to go, but of course this is running out right now, so it's not a true touch off on the diameter. This measurement here is a little bit inconsistent, right, to the actual sizes that we're going to be getting when we remove material on here. So really what we'd want to do is take a skim cut and then measure that, because that will be running concentric to the setup and we can trust that a little bit more. But 225 is about what we're going for. So I'm going to take cuts of 100 thousandths at a time. So move in from my 0, 100 thousandths. Now it's important to know that this dial here is graduated in thousandths of an inch on the diameter. So when you turn the dial 10 thousandths of an inch, it actually only moves the tool 5 thousandths of an inch in this direction. Because since the part is spinning, whatever we take off of one side, we also take off of the other, right? So we take 5 thousandths off of both sides. I mean, it's 360 degrees, so every 180 degree opposing point gets the same amount removed from it, right? So if we take 5 thousandths off of all sides, it's 10 thousandths off of the diameter if we measure across the part on its diameter, okay? Now this is an important point to know, because when I say we're going to take 100 thousandths of an inch off of the diameter of the part, we're actually only moving in 50 thousandths. So what the tool actually sees is only a 50 thousandths cut. Okay, so the depth of cut is typically given as a radial dimension, but our dials are graduated in thousandths of an inch on the diameter. Okay, just an important nuance to know. Okay, I'm going to set my feed rate to 7 thousandths of an inch because this is a roughing cut. LCS 8W right here. So that's L for low, C, S, 8, and W. Okay, make sure I'm feeding the correct direction. Okay, that's the right direction. Going to give it some coolant, and let's go. Okay, I'm going to stop it right there. You can see that we actually are not, we took this down from 1 inch to 900 thousandths, and over here we've got 875, right? And so, yeah, we're not, once we get past this point right here, we're not going to be cutting anymore. We're just cutting air. Okay, we have to take another cut to get it down a little bit more. Okay, so I'm going to back it off 1 revolution. Come back to my starting point. And you can see that those chips really didn't look very good. I mean, these chips right here, coming off kind of long and spindly and jagged, and I think this tool really doesn't like taking this deep cut on the steel. Let's try a 50 thousandths cut. So move back in my 100 thousandths, or sorry, my 1 full revolution to 100 thousandths where I took my last cut. So now I'm going to take a cut of 50 and let's see how it behaves. Oh yeah, that's loads better. Just much better chip control on this. You know, it depends on the tool geometry, the material, a number of things, but this is looking pretty good. It doesn't take me that much longer to take that extra cut, so I'm going to take 50. Okay, now I can see, boom, 0, 1, and stop it right there. Okay, so I saw it hit the plunger down here, right? It went to 0, I waited another revolution to the second 0, and I stopped it right before the third 0, okay? Then I'm going to feed it by hand, because it's very difficult to actually stop it right on the 0, okay? So we're not going to play roulette with our parts here. We're going to stop it a little shy, maybe 20 thousandths shy or something, and feed it the rest of the way by hand with the carriage until we hit the 0. And now we can back this off our 1 full revolution, go back to the start. Okay, so you can see that that surface finish is pretty poor, okay? And that's just because we're taking nice big roughing cuts. Let me just take a measurement now to make sure that we are where we need to be. So that says about 850 thousandths. Yeah, so we're right on course for having to take, what is that, 75 thousandths to get to 775. I'll just take that all in one go. So go back to where I took my last cut. Okay, I'm going to go another 50, 60, 70, and 75 right there, okay, to leave 30 thousandths on the final. Okay, you know, at this point, you're really going to want to make sure that you don't hit the surface on the cone of the live center with your tool, right? Because you can easily start scratching this up, and if you damage this surface, this is not going to work very well as a fixturing surface, right? Because then it's going to be all chewed up, obviously. Okay, so just watch out for clearance issues here on the back side of the tool. All right, let's engage. Remember that this is all about just maximum material removal rate. Okay, here we are. We're about to hit the plunger. 0, 1, stop. Feed it the rest of the way to the 0. Pull it out. Back to the start. So yeah, we're just looking for maximum material removal rate. But we also have to watch out for chip control a little bit, right? So we don't want nasty, jagged chips, you know, that are difficult to control. We don't want to burn the tool out prematurely, okay? Because we're hoping to be able to just transition directly into finish cuts right now and still get a good finish. Let me go ahead and take another measurement on here, but now we're going to switch to a micrometer. Okay. I'm going to rock it around a little bit, make sure I'm on that high spot. Use the ratchet. Okay, and that's telling me not 775, but 774. 750 plus 24 right there. That's pretty good. Okay. Something worth mentioning here is that on a long diameter like this that's held between centers, you really should measure in 2 or 3 places along the length of the diameter and make sure those measurements agree to each other within a thousandth of an inch or so. This is a way to check for taper on the part, because it's possible that the center axis of the tailstock and the center axis of the spindle aren't perfectly coaxial to one another, in which case one end of the part would be kicked out closer to the cutting tool than the other, resulting in that end being cut to a smaller diameter. Although there is a way to adjust the position of the tailstock to correct for this error, I'm not really going to go into it because we don't expect you to learn how to do this until the more advanced classes. But if you find that your machine is cutting a taper, let your instructor know. So 774 minus 745, which is our target, but actually it's 740 and 6/10 up to 750. Right, so this is just the middle of the range, so that's what we're going to shoot for. That's 29 thousandths, right? So it's really close to what we were looking for beforehand. So to make this easy, I'm going to take a cut of 15 thousandths, okay, as my second to last cut, and then I'm going to measure this again and take whatever the micrometer tells me to take as my finish cut, okay? So I always do like 2 finish cuts, 1 second to last cut and 1 last cut, okay, at exactly the same settings. That way I know that, I know what surface finish I'm going to get. I also know that I can trust the dial that whatever I tell it to take off, it's going to take that amount off because, the surface that I'm measuring was taken at exactly the same settings as the cut that I'm about to take. So turn this back on. Go back into where I took this last cut. Okay. Now I'm going to go another 15 thousandths, 5, 10, 15. I'm going to slow the feed rate down to, let's say, 3 thousandths. LCT4W. That's L for low, C, T, 4, and W. A little coolant, and away it goes. Okay, getting close to the plunger now. Okay, that's first 0, second 0, and right there. And then go to the 0 by hand. I'm going to stop it right there. Okay. Now remember, on my last cut, I don't back the cross slide out, okay? That's just so that I don't introduce any even remote errors that are possible when you move the tool in and out. Okay, that surface finish turned out way nicer. Way nicer than before, right? What an amazing difference it makes just to take a smaller depth of cut and to feed it slower, right? Really big difference. All right, let's take a measurement. All right, and that is telling me 750 plus 10, so 760 thousandths. Nearly on the money there. Okay, so 760 minus 745, 15 thousandths, okay? So I'm going to trust that number. Okay, turn this on again. Go in from where I am right now, 15 thousandths, 5, 10, 15, and engage. Now, the nice thing about already having a shoulder established at the correct position, right, is that I can use that as a visual indicator of when to stop. Like right there, okay, I haven't hit my shoulder yet, so I know that I'm not to my 0. And it looks like that was, again, about 20 thousandths shy of the 0. so I can just feed the rest of the way, okay, and stop it right there. All right, let's take a measurement. $7.25 plus $27.45 on the money. Perfect. Okay. Now you can see that I didn't back off my tool just in case I bungled this up really badly and needed to go in and take another cut. I didn't want to lose my position, but this is good and done. So what I'm going to do is go ahead and turn this back on and then feed the tool out this way just to clean up that shoulder. And back to the start position. Clean that off. Okay, so for the 6/18 diameter with the 1-inch length, we're going to do basically the same sequence of operations. So let's run through it. I'm going to position the tool so that it's in front of that face. Then I'm going to move the carriage to the left until it just touches off. Okay, right there. Pull it back, stop. Okay, we're going to take the 1, 2, 3 block, and it's going to be the 1-inch dimension now. Bump that up against the front of the carriage. Move that dial indicator in. Okay, so here it's not touching, and then there's first 0, second 0, and third 0 right there. Okay. Now when I take this out and put it back in, it should repeat to the 0, and it does. Good. Okay, so I'm going to go ahead and move the carriage over to where the 0 on my indicator should be. So here we go. It's the first 0, second 0, third 0, so 2 full revolutions there. Okay. Double check. That certainly looks like 1 inch. Okay. Turn this thing on. Feed in. Okay, make a little witness mark right there. Come back to the start of the part, but over top of the diameter, and I'm going to feed the tool in until I just take a tiny little cut. Okay, right there. Move the tool off. I'm going to re-zero just so we can start from scratch here. So I knew that this was 7.45 on the money, right? And so I need to go to 6.18. So that's 7.45 minus 6.18 gives us 127. But I'm going to take 30 thousandths less than that, right? So 97, right? So let's just take 2 cuts of 50 thousandths, make it easy. Okay, I'm going to go in 50. Right there, get to the start of the cut. I'm going to go back to 7 thousandths per revolution for my feed rate. So LCS8W. Here we go. Okay, 0, second 0, and right there, about 15 thousandths short. Move to that third 0, 2 full revolutions. Back off 1 revolution on the cross feed. Back to the start of the cut. Back in my 1 revolution. Remember, we do this in order to move the tool away from the part and in order to account for the backlash. Okay, then I'm going to go another 50 thousandths. Okay, right there. And engage the cut. Stop it by I. There it is. Okay, that was about 40 thousandths away, no big deal. There we go. Back it off and back to the start. Okay, time to take a measurement. Okay, here we go. Okay, and that says 625 plus 20 and a half, so 645 and a half. So 645 thousandths minus 618, okay, 27 thousandths. So, let's make it easy. Let's take a 15 thousandths cut, and then we should have 12 thousandths left over. Okay, turn this back on. Okay, so back in that one revolution to where I took that last cut, plus another 5, 10, 15 thousandths. Slow down the feed rate to 3 thousandths per revolution, LCT4W, LCT4W, and take the cut. Okay, here we go, pretty close. And stop it right there. Move over the remaining to 0. Go ahead and turn it off. Okay, move the tool off the part. Get all the chips off. Take another measurement. Right there. Micrometer says 625 plus somewhere between 6 and 7. So 625 plus 6, 631. Okay. So 631 minus 618, 13 thousandths. Okay. So turn this on, and I'm going to go in 13 thousandths. That's 5, 10, and then 3 of these little graduations here. 1, 2. It can be a little bit difficult to see those. Do your best. And right there. Okay, move the rest of the way to my 0. Okay, and now I'm going to, I'm going to go ahead and stop this and check it before I pull back on the cross slide. This one should just be to verify that we got where we want it to be. But you never know. Sometimes you don't hit it for whatever reason. Maybe you knocked something. Like, one thing that's happened to me before is I'll accidentally knock this handle right here, and that moves the compound, right? And then I lose my position, both in left to right and my position for the diameter. And luckily I hit it so that it backed off a little bit instead of going in a little bit too much. But this definitely happens, right? Okay, so there it says 619 thousandths. 619. That makes sense because we were basing all of our numbers off of, we were kind of in the middle of 2 numbers and I took the smaller number there, right? So it makes sense that we would land right around 1/1000th of an inch over our target value. That's definitely within tolerance, right? 618. So actually 618 is sort of just a reference number, but we're trying to be between 611 and 3/10 and 623 and 4/10, with 618 sort of in the middle of that range. So we're definitely within our size range here. Okay, going to go ahead and turn this back on and feed the tool out just to clean up that shoulder. And that's it, folks. That's it. I'm going to go ahead and take this thing out, so back that off. So now you can see that this part, well, it looks like the picture, doesn't it? That's always good. So we already checked the diameters on here. We did not check those lengths. Let me go ahead and do that just with the dial caliper. So I'm going to use the depth attachment on the caliper here. Stick that out from the end of the part. You got to make sure that you don't get this cocked out at an angle either this way or this way. right? So I kind of just like follow the side of the cylinder there. You also remember that there's the tool nose left a little bit of a radius in that corner, right? And so you want to measure sort of out here towards the outside of the shoulder so that you can, you get an accurate reading instead of just bottoming out on the radius. Okay, and that's telling me, yeah, 3 inches and like 1/1000 or 2/1000. I mean, it's not the most accurate measurement in the world, but that's certainly good enough. Okay, and then let's check this 1-inch dimension here. Yeah, and that's also telling me, yeah, 1 inch on the money according to the dial caliper. So great. Okay, so this is actually ready for the next stage, grooving and chamfering. And that's going to be the next video in the series. I'll see you then.